Okay, this is section 6-3, and it's called Counting Strings with Replacement. And in a little bit, I'm going to explain what strings is and what it means, the replacement part also means. Okay, but before we get to that, I want to talk about the multiplication counting principle. It's actually a pretty easy concept to understand, and it says let A and B be any finite set the number of ways to choose one element from A and B is the number of elements in A times the number of elements in B. So you're multiplying however many outcomes there are in A times the number of outcomes there are in B. So it's a pretty easy concept. So the Blue Yonder Travel Company offers package vacations with a choice of economy class or business class flights and 3 options for accommodation: 3-star, 4-star, or 5-star. The tree diagram below shows the different possibilities. So we have a vacation. We have 2 options. We can go business class or we can go economy class. Okay? And then after we take that flight, then we can choose from a 3-star, 4-star, 5-star hotel. So if you think about what we would have done, earlier in this week, earlier in this chapter, we would have written down all the different outcomes. We would have said business, 5-star, business, 4-star, business, 3-star. Then you would have done economy, 5-star, economy, 4-star, economy, 3-star. And we could have seen all of our sample space and all of our different options. But today, we're just wanting to know how many different possibilities are there going to be. Not necessarily what they are, but how many are there. And so you take the number of outcomes in the first set. So there are 2 outcomes here. And then for the second set, there are 3 outcomes. You're either getting 5, 4, or 3-star. And you multiply those together and you have 6 possible vacations. So we're just trying to figure out how many are there. And so you can see in example 1 that what we did before, where we listed out the sample space, could get a little bit crazy. So let's look at this. A popular game show features a spinner divided into 24 congruent sectors and numbered something like the wheel shown at the right. So if you see some kind of game show that might look like this, like Wheel of Fortune, for example, the spinner cannot stop on a boundary line. Okay, then you spin it again. Describe the sample space, S, for the experiment and determine the number of elements in the sample space. So we're spinning this spinner twice. And so, for example, the first time it might land on 250, and the second time it might land on 250 again. So that would be 1 element in the sample space. The first time it might land on 250, and the second time it might land on 100, or 250 and then 500 and then 250. So think about how many options are there for the first spin. So X is the first spin. And there are 24 possibilities for the first spin alone. Okay, and then the second spin, there are 24 possibilities again. Trying to write fast, spelling things wrong, I'm sure. Okay, so there's 24 for the first one, 24 for the second one. So if we use this multiplication counting principle, 24 times 24, we get 576 different total possibilities. Okay, you wouldn't want to write those all out like we have been doing before. Okay, so we are not going to write them all out. That would take you all day. So we're just wanting to know how many are there. Okay, so a string, actually another way you can think of it is 24 twice, or 24 squared. Okay, we'll come up, we'll do something else like that in a minute. We get strings when the elements in a problem must be ordered. So just like yesterday and previous days when we roll one dice and then roll another dice, we're creating strings. We get a 1 and then a 6. That's a string. And then we get a 2 and a 5. That's a string. The order matters, okay, when we're ordering this. Okay, the length of the string is the number of elements in the string. So, for example, when we did the dice, 1, 1, 1, 2, 1, 3. These are all of my strings, and each one has a length of 2. Okay, example 2. On a 28-question multiple-choice mathematics test, each question has 5 choices. How many possible completed answer sheets are there? So if you think of this like, oh, I'm going to go into this test and guess every question, what's the chances of me getting it right? So I'm just going to show you how we do this. So if question number 1 has A, B, C, D, E, okay? And then question number 2 also has, that's my set. Those are my options for question number 1. Question number 2 also has A, B, C, D, E. And I would do this 28 times. So one possibility would be I would guess A, 28 times. Okay, another possibility would be I guess A 27 times and then guess a B on the last one. So we can see these are strings. A, that's a string of length 28 because I would do it 28 times. Okay, so if each option, there's 5 options for number 1 and 5 options for number 2 and 5 options for number 3. We could do 5 times 5 times 5 times 5 times 5, but that would take us forever to put that in our calculator. So we just do 5 to the 28th power. Okay, whatever that is. I'm not even put on there. The calculator may not even, it may give you something in scientific notation. So we're just going to leave it like that. Okay, and then it asks, if you guess randomly on each question, what's the probability of answering all 28 questions correctly? Okay, so that would be 1 out of that number, 5 to the 28th power, whatever that is. All right, so we have this theorem, and this is about strings with replacement. So I'll also explain what replacement means. Let S be the set of elements. Let S equal the set of elements that has n options. Okay, S is the set that has n options. Then there are n to the k possible strings with replacement. Sorry, n to the k possible strings with replacement of length k. So it's just like this one. So n is the number of options, so there's 5 options, and k is the length of the option. So k in this case was 28 because we had the string was 28 questions long. A. So there's 28 of those. So 5 options with a length of 28. That's where the n to the k power came from. So for example 3, in a certain state, license plates have 2 letters followed by 4 digits from 0 to 9. How many license plates are possible? Okay, so we have letters, 2 letters. So letter 1, letter 2, and then digit 1, number 2, number 3, and number 4. Okay, so we're going to look at all of these. So how many different letters are there for the first choice? There are 26. Okay, so here's where this with replacement comes in. Sometimes there might be 26 letters for the first one, and then you're not allowed to use the letters again, in which case there would only be 25 letters for the second one. And we'll talk about that later. But in this case, we're talking about with replacement, so you're allowed to use the same letters twice. So 26 for the first one, 26 for the second one. And then the digits are 0 to 9, which is 10 choices. 10 choices for the second one, 10 choices for the third one, 10 choices for the fourth one. All right, so there's 26 twice and 10 4 times. And if we multiply those numbers together, we get our total number of license plates, 6,760,000. Again, we wouldn't want to write out those strings because they would be so long. Okay, you might have AA0000. That would be one string. So if your letters were 0000, that could be one license plate. AA0001, AA0002. There would end up being 6,760,000 strings that we would write out. Obviously, we don't want to do that. Okay, so independent events are events A and B are independent events if and only if the probability of the intersection of those two sets is equal to the probability of A times the probability of B. So that means, so this is what's important, the probability of the second event is not affected by the first. So like I was saying up here, letter number 1, there's 26 options. And for the second letter, I still have 26 options because what happened for this first one does not affect what happens for the second one. These are independent events. And I actually think we're going to have to write this again. I put this in the wrong spot, but that's okay. This is the idea. The probability of the second is not affected by the first. Okay, example 4. The spinner shown is used in a carnival game. It is assumed to be fair, so the spinner has the same probability of landing on each sector. If the spinner lands on an edge, the spin does not count. The game consists of 2 spins. You win if the first spin stops on an even number and the second spin stops on a multiple of 3. So let's think about how we win. So we win if the first spin is an even number and the second spin is a multiple of 3. So we want to know, what is the probability that event A and event B overlap each other? That's what we're trying to find, okay? And we know that one spin does not affect the other spin. This is a fair spinner. So we do the first one, then we do the second one, and the first one does not affect the second one. So that means if we're trying to find, if these are independent events and we're trying to find the probability that they both happen, then we just take the probability of the first one and multiply it by the probability of the second one. And that is going to give us our chance of winning. Okay, so the probability of getting an even number, let's find that one. Probability of an even number. Okay, there are 3 even numbers, 2, 4, and 6. 3 out of those 6 are even numbers. And the second spin is a multiple of 3.